Okay, so yesterday we talked about the history of the periodic table, and we went through different scientists' contributions and how they took the elements and put them into an order and then reorganized that order, and then they added a few new things to it, like the noble gases and the actinides. So yesterday we learned how it became the periodic table, how its history has changed to get us to the modern periodic table that we're all familiar with. What we're going to go over today is a little bit more, how is it set up? What are different regions? How is it organized? What's the structure of the periodic table? Just small different pieces of information that we can get from it. So we're going to start with the basic structure of the table. And we learned yesterday that the elements are arranged in order of increasing atomic number. Remember, the atomic number tells you the number of protons. So the elements are put in order of how many protons they have. There are 7 rows. Rows go across. These rows are called periods. There are 18 columns. Columns go up and down. And the columns are called groups or families. 7 periods, 18 groups. And then at the bottom, of course, like we talked about yesterday, there's those 2 rows that are called the lanthanides and the actinides. There are also 3 different sections of the periodic table. And if you look at the periodic table, you can probably figure out what those sections are. They're almost like our blocks that we learned from our electron stuff. A little bit different than that, but they're pretty close to that. First one we call the representative elements, and that includes groups 1 and 2 and 13 through 18. These are otherwise known as the S block and the P block. Those 2 blocks go together to make the representative elements. Then we have the transition metals. These are groups 3 through 12. Otherwise known as the D block. And hopefully you remember from electron stuff, these are the elements that are pretty much in the center of the periodic table. Things like chromium and copper and zinc, those are all transition metals, that middle section. The third section we have is called the inner transition metals. And these are those 2 rows on the bottom. So this is the F block. Which includes the lanthanides and the actinides. We call them the lanthanides and the actinides because they're named after the first element in that series or in that row. The first element in the bottom row is lanthanum. And then underneath that is actinium. So we name those 2 rows after the first element in each one. Yeah, it is definitely possible for more elements to be discovered. In fact, anything on the periodic table that's got a UU and then a letter like UUO, UUT, that's a relatively new element that they haven't decided what to name it yet. So they're making new elements in like a particle accelerator. They can smash atoms together and get a higher number of protons than what they had before. So they're currently making new elements. The new elements that they make aren't very stable. So that means they're usually radioactive and they will decay very quickly. So they only hang around for a really small portion of time. It's hard to figure out what their properties are going to be, solid, liquid, are they metallic or not, but we do know of their existence, or we're able to create their existence for a split second of time. So it's almost filled in now. It used to be a blank space underneath where lead and bismuth and polonium are, elements 112 through about 118. That used to be all blank. When I took high school chemistry, there wasn't anything in that space. And now we know that there are elements that go there, although a lot of them haven't been named yet. It's actually kind of a big deal when you get to name an element. Everybody wants to name the element after their college or their research group, and so there's usually quite an argument in the scientific community over what the new element should be named and who or what it should be named after. So it can take years to prove the existence of that element and then decide on what its name is going to be. Okay, we can also take the periodic table and divide it into different regions, and these regions are different kinds of elements. So up to this point, we've said the S block and the P block are the representative elements, the D block is transition metals, the F block is intertransition metals. What we'll do with these four regions is, instead of dividing it by electron configurations, we'll divide the periodic table more by properties of elements. So what kinds of elements get grouped together? First, we'll start with the metals. This is the largest region of the periodic table. Most of the elements that we know of are metals. And anything that is to the left of the staircase qualifies as a metal. And we'll talk about what that means after you get this written down. There should be a periodic table at the back of your notes packet, so turn and look at it for a second. On that periodic table, towards the right-hand side, there should be a heavy black line that kind of goes down in stair steps from between boron and carbon all the way down to about iodine. You see the heavy black line that takes the stair steps down? Yeah. That's the cutoff for which elements are metallic and which ones are not. So the largest region would include the metals. Anything to the left of the staircase or underneath the staircase qualifies as a metal. All metals are solids except for one. So go back to your other page. We're going to continue with some properties of metals. All metals are solids at room temperature and standard pressure, except for one. The one that's not is mercury. What state is mercury in? A liquid. And that's the only one that's a liquid. All metals are good conductors of heat and electricity. Some metals conduct better than others, but all of them are conductors. All of them have a property that may be talked about in earth science called luster. Did you guys go over this when you did minerals last year? No? Luster refers to whether or not an element or a substance is shiny. So you think about a typical metallic appearance would be like a penny or a quarter or the legs on your desk. Something that's very shiny and reflects light. That property is called luster. All metals have the capability or the potential to be shiny or lustrous. Sometimes you have to polish them up. They're not all lustrous in their natural state, but they all have that property. All metals are also ductile. Ductile is usually a new word. It means stretchable. This is how they can take metals like copper and stretch them into thin wires that you can run electricity through. Sometimes you have to heat them up a little bit to get them to be warmer and pliable, and then you can stretch them out into a wire. All metals are ductile. Metals are also malleable. Malleable means they are able to be flattened. Think about aluminum foil. All metals have the ability to be flattened into a thin sheet. The way that I remember what these two words mean, malleable to me looks like the word mallet. If I'm going to hit something with a mallet, I'm going to be flattening it out. And then ductile has to be the other one. Like you're going to stretch it into a duct, like a heating duct, usually long and skinny. The next region is called the nonmetals. Nonmetals are located to the right of the staircase. Nonmetals come in all different states of matter. There are some that are solids, there's one that's a liquid, and there are some that are gases. As you might expect, nonmetals tend to have opposite properties of metals. So nonmetals have low conductivity of heat and electricity. They are not very good conductors, which would make them pretty good insulators. An insulator is the opposite of a conductor. Anybody know what element this is in the picture? Sulfur. It is sulfur. This is the natural picture of sulfur, so it's its natural crystalline state. You could actually find this potentially if you were mining in the right location. You could find natural sulfur like that. Nonmetals typically have a low luster, or they're not very lustrous. It means they're typically not very shiny. They are also very brittle solids. This is the opposite of metals. Metals you can stretch, metals you can flatten, and they don't just fall apart. If you take a hammer and you dent the side of your car, it doesn't just break into a million pieces, it just flattens a little bit or leaves a dent. Nonmetals are different. If you took this piece of sulfur and you hit it with a hammer, it would just shatter into a million pieces. They make very brittle solids. The third region is called the metalloids, or it's called the semi-metals. Both words mean the same thing, and they refer to the region of the periodic table that is right on the staircase. So elements that are directly touching the staircase are metalloids or semi-metals. They're called semi-metals because they share some properties of metals and some properties of nonmetals. They share properties of both sides of the stairs. Which means they are semiconductors. They kind of conduct heat and electricity. This, in fact, makes them very useful for things like computer chips. What are computer chips made out of? Silicon. And this is actually a picture of silicon in its natural state. Notice it's kind of shiny, but it looks more like the sulfur picture than it does the picture we had of the metals. Silicon is a semiconductor. It kind of conducts electricity. That makes it very useful for using in computer chips and other things. Last region of the periodic table that's kind of all by itself is the noble gases. This is just one column. It's group 18, the column on the right-hand side. All of the noble gases are, of course, gases. They are extremely unreactive. That has a lot to do with their electron configuration, which we'll talk about in a couple of months. They are extremely unreactive. They don't make compounds very easily. And some examples. Neon we've got at the bottom. That's the emission tube that you saw in your lab a few days ago. What's the one we put in balloons? Helium. Okay, a couple other pieces of information we need to know. Phases at STP. STP stands for Standard Temperature and Pressure. Standard temperature is 0 degrees Celsius. That's the temperature that water freezes at. Standard pressure is 1 atm. An atm is an atmosphere. Standard pressure is the amount of pressure that you live under all the time. There is 1 atmosphere above your head, and it pushes down on you. 1 atmosphere is the pressure that you live under all the time. So STP, it's kind of like normal conditions or pretty usual conditions. 0 degrees C is maybe a little bit colder than we normally live under, but it also makes for a very even number to use for our standard temperature. So what phases of elements do we have at STP? There are only 2 liquids that we know of. They are mercury, which we talked about, that's the metal. And we also talked about 1 non-metal being a liquid, and that's bromine. There are several gases. They include nitrogen, oxygen, fluorine, chlorine, hydrogen, and all of the noble gases. Everything else is a solid at STP. One other piece of information we need to know. There are 7 gases that are called diatomic. What does that prefix mean usually? Di means 2. Di means 2. So diatomic would be 2 atoms. There are 7 gases that when they are found naturally, they are found as pairs. It's a pair of 2 atoms together rather than just single atoms. 7 of the naturally found gases are diatomic. That means they're found in pairs, or they're found as molecules of 2 atoms bonded together. This is why when you see the formula for oxygen, it's not just O, it's O2. The list of the 7 diatomic gases include bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. And the easiest way I have ever found to remember what those 7 are is to take the symbols and turn it into a word. So if you were going to take the symbols in that order and turn it into a word, it would say Brinkelhoff. Doesn't really sound like a word, kind of just sounds funny. But if you can remember Brinkelhoff, then you'll remember all 7 of the diatomic elements. And this is something that you will need to memorize for your test. So you might want to mark it with a little star. This will be on the test. Make sure you know these 7 elements. Okay, that should be it for today. Yes.
I don't get the part of the